Hello there, everybody, and welcome. This is Professor Thayer with you here today to talk to you about quantum mechanics again today. So this will be lecture 3, and today we're going to focus on solving the classical wave equation. Now you might be wondering, why are we solving this? It's not really quantum mechanics, and that's a fair point. It really isn't, because it's, well, classical mechanics. But this is going to bring up the idea of this separation of variables. And this is a very important point that comes up over and over again as we solve quantum mechanical problems of varying degrees of difficulty. Being able to separate out those variables and break it down into smaller problems that we're actually able to solve. So as we'll see today, one of the major things that happens when we solve the classical wave equation is, first of all, we have now an equation of x and t that is the position and the time, whereas when we were talking about just solving the second order homogeneous linear differential equations, we just had one variable, and so it was fairly straightforward on how to solve this thing. But now we're going to have two variables. So how are we exactly going to deal with this? Well, the simple answer is that actually we just will divide it into two separate problems, and then we'll just solve each of the problems separately. Right? So if you can divide it up and x and t are separable, that is, you can divide into two differential equations, then you could just solve each one as though it were only one equation by using the methods that we talked about last time. And that's basically the strategy on how to solve these things. All right, so we will take a look at that, and then the rest of the problem then consists of dealing with the boundary conditions. Now, this was actually a pretty long topic, so I expect we're probably going to need 2 lectures to cover this whole thing. So why don't we go ahead and get into talking about what the problem actually looks like and solving with the separability, and yeah, we'll see how far we get and what topics we will lead for the next time. So there's all kinds of exciting things about considering all the boundary conditions. Oh yes, and there'll be the separation constant K, which is going to also make things more exciting that we do actually need to deal with. All right, so let's get started. I'm going to go ahead and share my screen as usual. I encourage you to follow along taking your notes. I'm going to turn off my video and share that screen and get started. All right, so let's turn the screen off, but let's share screen. There we go. Full screen, start sharing now. Great. Okay, you are sharing screen. Good. All right. So hopefully now you can see this, and hopefully I'm improving my skills at working with all this technology stuff. All right. And let me just make this all full screen. The Zoom menu were not in the way. That would be super helpful. All right. Can you open up and go full screen? Full screen. There we go. All right. Classical wave equation. All right, so the first thing we should probably do is we should probably just get clear on what exactly the classic wave equation is describing. So let's go ahead and start by making a little diagram of what all this actually is. So it's actually a pretty simple thing. I mean, that's the amazing thing about physics, is that you start off just trying to describe something nice and easy, and it quickly gets complicated. All right, so we have some x-axis here, and we have some position at 0, and we have some position at L for the length of the string, okay? And you have some wave propagation along the x-axis, and the string is going to be bound. So I play violin. I like to think about a violin string, but maybe you play another instrument, or maybe you don't play any instrument at all. But anyways, this is the basic idea, that there is some height here, right? Some displacement. And so the u of x and t is describing that displacement. So what our scenario is here is we have a vibrating string. fixed at endpoints 0 and L. Zero and L. So what this means is that on the x-axis, right, the string is bound at the 0, right, at the origin, and then it goes up to some length L, which represents the length of the string, and then we have an amplitude. Should I remember that means the displacement of the wave, u of x and t is a function of position, and time. So position x and time t. Great. And so that equation is given by this. And guess what? It's a differential equation. All right, d squared u second derivative, right? U of x and t over dx squared equals 1 over b squared d squared u of x and t over dt squared. This is the classical wave equation. So if you take an intro physics course, you are quite likely to encounter this as well. And the v is the velocity. And of course, velocity has a magnitude and direction, but since it's kind of fixed, it's really more like the speed of the disturbance along a string. All right. Now we have the bounding conditions, which we've already mentioned. What are the bounding conditions? U of 0 t equals 0, and U of L and t equals 0. And these are both for all t. All right, what exactly does that mean? How did we know we could write that? All right, well, just taking a little look back at our diagram here, what this says is that it says that the displacement, that is the height at which the wave is vibrating, is gonna be 0 when? Well, look at it's bound on the lower and the upper end, and it's always bound in all time, right? So what this says, okay, this is x and t, right? So the x coordinate is this one here. So when the x coordinate is 0, that's this end right down here. You're at this bound end right in this place right here, okay, that the displacement is gonna be 0. And that is true for any time because the wave is always, because the string is always bound. It's all, you know, it's not gonna be jumping off. And the same thing is for the other end. Okay, so this says at the position x, at the length of the string, that is the other side of the string, which is also bound, for any time, the displacement is going to be 0, and that's because this wave is being displaced above. It's also, of course, could be displaced below. If it's vibrating, you would also have another displacement down here, right? There's also this one happening as it vibrates. And if you've ever seen any of those pictures of, say, like a guitar string, which is much larger and has a good displacement, with the strobe lights, you can see how that looks when you're playing a sound. So that's what we have here for our bounds. Now this will become important because as we saw, we can use the bound conditions in order to solve for the integration constants. All right. So basically what all this means is it means the string is fixed at the ends, right? It's attached. That's what it means. And that's how we can mathematically write that. All right, good. So now that we have the right picture in mind, we can start thinking about what we can do here. So it's more complicated than solving just a second order homogeneous linear equation because the displacement equation is a function of two variables. So notice that before we had only one variable, we just had x, right? But look at this one, it's got two variables in there, so it's gonna be harder. So like we said, we're going to need to apply the principles of separability. So u is a function of both x and t. So in order to solve, we will need to separate out each one and solve separately. They will be related by a constant k, which will then become important later on. All right. So now what we need to do is we need to work on the separability. All right, so here's our equation. This thing up here, two variables, cannot solve with two variables using anything we've done before. So next we're going to need to apply separability. So let's do it. Step one. Place to start. Separability assumption. If you've taken the multivariable calculus, you might know a little bit about what I'm talking about here. So terms are separable if you only have a single variable in each term, because then you could divide them onto a different half of the equation. And if you had some term that had both variables in it, both the x and the t, it wouldn't be separable. Okay, so we're going to assume that u of x and t factors into a function, two parts, x of x and t of t. Parts. Function x of x times a function t of t. So what this basically means is we have some function, and that the name of that function is just going to be this cap x, that is a function of the position information, which is the little x, times some function t, which is our time function, which is a function of the t, which is the actual t variable. So if that were true, then we could write u of x and t, that's the original function that tells about the displacement, equals some function x of x times some function t of t. That's the separability assumption. Is captured in that equation right there. All right, so we'll assume that's true. And that actually can be demonstrated mathematically, but we can actually see this by inspection. Okay, well, great. So now let's go ahead and do it to our equation. So here we have e squared u of x and t over dx squared equals 1 over v squared times d squared of u of x and t over dt squared. This is the original function for this string. And this is from above. All right, great. Now we have our separability assumption right here. So the next, all right, so this is our step one. You make the separability assumption. We just made it. All right. Now step two of solving this thing is we're going to factor out any constants from inside the derivative operator. It's the derivative operator. That's this derivative thing right here. Okay, so these are being operated on by this operator. The d squared over dx squared is our derivative operator. There's another one. Now, if you've taken multivariable calculus, you might be aware that when you're taking a partial derivative, that you can hold something fixed, and then it becomes more or less an effective constant while you're holding it fixed. We're going to be applying a similar idea here. If you don't know exactly what that means, hopefully this explanation will help. All right, so the next thing we need to do, though, is we need to substitute in. Okay. Here, actually, I think I'm gonna do it proof style. All right, so let's do it like this. So what I'm gonna do is I'm gonna do d squared u of no, that's not what I'm gonna do. What I'm gonna do is I'm gonna go ahead and put these big old rectangular or square brackets here, and I'm going to substitute in because I'm going to substitute in a whole equation. Okay, so here we have this of u of x and t, but now I have a definition of u of x and t, which is x of x, right, times t of t, like so. I'm going to put those in the square brackets just so I remember that I substituted something in. It's very easy for me now to see where I substituted something. Equals 1 over b squared. So I'm just copying down, and now I'm going to substitute in d squared, and let's put in, okay, x of x times t of t. All right, there we go. Again, a nice big square brackets so I can easily see where I substituted something in and over dt squared. All right, good. Now, there's some important things we should notice. This side, over on the left, this side is about x because we're taking the derivative with respect to x. This side is with respect to WRT with respect to x. And t of t doesn't have any x in it. T of t doesn't any x in it. Why does that matter? Because we said that step 2 is about factoring out any constants, and we were just talking about how we think about this in calculus. Okay, so if t of t is a function with respect to t, and on this side, we're taking the derivative with respect to only x, then t of t is basically going to be a constant on this side. Similarly, on the right-hand side, this side is with respect to t. And x of t and x of x doesn't have any t in it. So the important thing about that is that on the respective sides, the constant part can be pulled out. So on their respective sides, constant part can be factored out. And that might include a function. Actually, it will. All right, so when we do like that, then what we can do is we can go ahead and factor these things out. So now what we can do is let's take a look at the left-hand side. So what's the constants on this side? Well, we just said t of t has nothing to do with x. So with regard to the derivative that's taking the derivative with respect to x, t of t is a constant. So I'm going to go ahead and pull t of t out. And now I can take d squared x of x over dx squared. And I'm just following along right from this line right up here, okay, equals. Now I'm gonna do the same thing from over here. All right, now this one does have some more normal looking constants. 1 over v squared should be recognizable as a constant. So just go ahead and pull that one along. But now look, we have this t of t and dt squared, right? So the t is the variable on this side. So that means that the x of x is not needed to be integrated, right? So this can come outside. So we'll factor that one out. And x of x times 1 over v squared would just be x of x over v squared, right? So I'm just gonna put my x of x over v squared times, now I'm gonna have my d squared t of x, t of t left inside over my dt squared. So that's what's left inside my derivative, this part of the function here, whereas this part is now factored out. All right, great. Now let's move on to step 3. So step 3 is divide both sides by u of x and t. U of x and t equals x of x times t of t. We have just one variable on each side. All right, that may seem like something that you're not allowed to do, so let's just talk about why that's allowed. So if you had an equation in math and you multiplied everything through by the same number on both sides of the equations, would it still be the same equation? Well, I mean, it would be equivalent because it would just be scaled up, right? You'd be multiplying by a scalar. Right. Well, division really is just another example of multiplication because you're just multiplying by 1 over a number for division. So really division is the same thing. So, well, why not divide by a whole function? Well, why not? You could divide by a whole function, and that's what we're going to do. So as long as whatever you do to the left-hand side, you also do to the right-hand side, that's an allowable operation, and it maintains the equivalence of what we've just done. So that's what we're going to do next. So let's bring this along, and then we're going to do our division. Okay, so I'm going to write it like this. T of t, right? That was our constant over something times d squared x of x over dx squared equals, now we've got our equation over here, x of x over v squared. Let's go ahead and make this line a little longer, anticipating what else I need to do. And then we just bring along the rest. D squared t of t over dt squared. All right, now so we're gonna divide out by this function right here. So to divide out means multiplying by 1 over it. So I'm just gonna put it in the denominator. All right, make my fraction line nice and large here. So we got x of x times t of t, and we're gonna do the same thing. Whatever you do to the left, you must also do to the right. X of x times t of t. All right, well then, that certainly makes an interesting situation because we have some canceling that we could do. So you could cancel numbers. You can also cancel whole functions. So why not? All right, so we have t of t in the numerator and the denominator here. So that one's gone. And I always like to make sure my canceling is nice and clear, what cancels with what. So sometimes I switch up the slant of my canceling sign just to make that clear. And so we also have canceling right there. So the interesting thing is that now on both sides of the equation, we're left only with one variable. The left-hand side has only x's, and the right-hand side has only t's for the variables. Here, let me also just make sure that it's really clear that that x also cancels, right? This whole thing, x of x. All right, just to be sure. All right, so now so this was by canceling. All right, so now the next thing we're gonna do is we're gonna just simplify this. All right, so we got rid of a bunch of the junk here. So we got 1 over x of x times d squared x of x dx squared equals 1 over v squared t of t times d squared t of t over dt squared. Oh, but Professor Thayer, look, you could have done some more canceling, right? Numerator and denominator, same thing. Don't forget that when it's inside an operator, that's not allowed, right? Because you're operating on it. It has to be factored out in order for the canceling to work. All right, so there we have our revised equation now. Okay, that's good. But all right, so what we want to notice here is this is all x variable on this side, and this side is all t variables. All right, great. So this shows that x and t, because we're able to divide them out, this shows that we can separate them x and t to opposite sides of the equation shows the separability assumption was valid. Great, it is separable. All right, next, step 4, set each side equal to a constant k. Why can I do that? Well, if two things are equal to each other, then they should be able to be, for example, solved for a number. And in order for the equation to be equal, that number that they each solve to would have to be the same. So you could think that number is k, it's just that we don't actually know what the answer is yet. I mean, maybe k is more complicated than just a number, but let's think about it in simple terms. And that's why that should hopefully make sense. All right, so the separability can only be true if the two sides are both equal to a constant k. So let's go ahead and take advantage of that. So we're going to have 1 over x of x d squared x of x over dx squared equals k, and 1 over, and I'm just pulling along from what's up here, v squared t of t times d squared t of t over dt squared equals k. And those k's have to be the same number, otherwise it wouldn't make sense. All right. Next, we'll need to subtract the k's to get the equations equal to 0. Why are we doing that? Well, it looked kind of like some equations with differentials in them. It looks sort of similar to what we were looking at last time. Well, that's exactly where we're going. Set the equations to 0. All right, well, how would that work? Well, we'd need to subtract k from this side of the equation, right? That would set it equal to 0, because then k would be on the other side of the equation. All right, well, let's do that then. So 1 over x of x times d squared x of x over dx squared minus k equals 0. And 1 over b squared t of t times d squared t of t over dt squared minus k equals 0. All right. Looking closer and closer to what we were working with last time. All right, step 6. Multiply to remove the denominator and make the leading coefficient 1. Remember, we talked about solving the linear homogeneous, the second order linear homogeneous differential equations, right? One of the things you have to do is have the leading coefficient be 1, and that's not 1, right? It needs to be set equal to 0. That's the homogeneous part of the equation. So now they're equal to 0, but they're not having leading coefficients of 1. So how would you do that? Well, let's take a look at the left-hand side first. We'd multiply out by x of x by all the terms. Step 6, multiply to remove the denominator and make the coefficient 1. To make the leading coefficient equal to 1. All right. So in this equation, what that means is it means we need to multiply out by x of x times the whole thing. 1 over x of x times d squared x of x over dx squared minus k equals 0. All right, and so then we'll distribute over this. So now we're gonna do x of x over x of x times d squared x of x over dx squared minus, now distribute it out, right? X of x times k equals x of x times 0. All right. So we have some simplifying we can do here. Great. So, okay, let's just write out how we did this. So this one was done by multiplying the whole equation. All right, and this one is distribute. All right, good. Next, we need to do some simplifying here. So I'm gonna just do this. Now the x of x's cancel out. And anything times 0 is just 0, right? So this whole thing is just gonna be equal to 0. All right, well, now let's rewrite that. It's gonna be a little simpler. Good. D squared x of x over dx squared minus x of x k equals 0. All right, let's simplify. But don't forget that we had 2 equations. So we need to do the same thing for the other equation. So let's go ahead and do it. So this one was the left hand. The left-hand side, right? Now we need to, so LHS left-hand side. Now we need to do the right-hand side. It's not sides of equations, but sides of my screen here. All right, so what's next? 1 over v squared t of t times d squared t of t over dt squared minus k equals 0, right? That's given above. And then we're gonna multiply out by the denominator. So we follow the same procedure. So we're gonna do v squared t of t times the whole thing, 1 over v squared t of t times dt of t, d squared over dt squared minus k equals 0. So we're gonna distribute, and this is multiplication. Next thing we do is we distribute this out. So now we have v squared t of t over v squared t of t times d squared t of t over dt squared minus v squared t of t times k equals 0 times v squared t of t. All right. Now again, we can do some simplifying. So this whole term goes to 0 by multiplication of 0. And the whole point of doing this is to cross this out and make the leading coefficient be 1. All right, now after that, we can write something quite a bit simpler. So this was a distribute. And then we finally will do the simplification step down here. So we got d squared t of t over dt squared minus v squared t of t times k equals 0. All right, great. So let's just step back for a moment here. We've now done separability. So let's just zoom out a little bit to see what exactly we have done here. All right. So we've talked about the this wave equation, which represents a standing wave on like a vibrating string, and we have this equation in two variables, x and t. And the problem is we don't know how to solve with two variables, but we know how to solve with one variable. So if I could get a second order linear homogeneous equation in just a single variable, then I could solve it. So if I could separate out the x and t, then I would be able to go ahead and do that solution. So that's what I've done. I've applied the separability assumption. And then because we were able to separate it out, we were able to demonstrate that in fact it was separable. And when we separated that out, we actually got two equations. And when we got those two equations, let's just find them up here. We have the solution from the left-hand side, which is this one right here, right? This simplified version, right? We have this equation for the x's, and we have this equation down here for the t's, right? This also is a simplify, so we'll just highlight this. All right, so that's what we have. We have an equation for x. And this one we have an equation for t. This is also simplified. Those are our two major results that we have so far. Now, about the k. Do you remember that when we did the separation that we did have a k, and those k's are the same k for both equations. So the equations are separated, but well, mostly. They are linked by that k. And so, well, what about that? Well, we need to make some considerations. Now, do you remember when we were solving last time the differential equations? We had this issue about the discriminant. And when we were talking about that discriminant, the sign of the discriminant became very important. And the reason why the sign of the discriminant is important is because, as you might recall, it determines which functional form of the solution we go to next, right? That was the multi-step process from the last time. And as it turns out, the sign of K is in fact going to determine the sign of the determinant. That determinant solving our linear homogeneous equations, the second order. Yeah, getting all those words in, I forget them sometimes. All right, so we're going to need to think about that. Okay, so let's just take some notes about this. We need to consider K, the separation constant. It links the two equations. They are mostly separate. At least separate enough to do the derivatives. All right. The sign of K will become important in determining the sign of the discriminant when we solve the second order blah 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 DQ. Okay. There are three cases. K equals 0. K is less than 0, or K is greater than 0. And we don't know which one it is. So we must solve all three possibilities. All right. And you have to do this for each side. So in other words, if you have the left-hand side and the right-hand side, and you have three cases, how many times do you need to solve the second order linear homogeneous differential equation? That's three cases times two sides. That's 6 times. That's a lot of solving equations. So this is why I said it's very important you ask about if you didn't understand the procedure last time, because you see that we are doing quite a lot. All right. And then step 7 of this whole thing is solve the second order linear homogeneous if equation according to C last time. Alrighty, well, there's no time, excuse me, like the present to go ahead and get started with that. So let's go ahead and start with the X equation. So we're going to start off like this. B squared x of x over dx squared minus kx. Let me make that a little bigger. A x of x equals 0. Right, this is from above. This is the position equation of. All right. And k is still unknown. Let us assume k equals 0. We don't know what it is. All right. Now what we're going to do is we're going to substitute that in. All right. So b squared of x over dx squared minus k times x of x oh, no, the whole point of this was to substitute in k is 0. Sorry, put a 0 there. 0 times x of x. Oh, no, it's no denominator anymore. That's gone. Equals 0. And I'm just copying along. And this was sub in a equals 0 assumption. This is actually pretty simple, so we could actually just okay, we could solve with the whole procedure. Last time we got lucky and it's simple. So we can take a shortcut. And just integrate. You're welcome to go ahead and solve it the long way if you prefer. All right, so what I'm going to do is this integral of d squared x of x over dx squared equals, right, this all cancels out, should be fairly obvious at this point. All right. Dx, right? So note the integral has their inverse operations. All right, so when we do that, what's going to happen is you're going to remove one power, right? Because you did one dx, you did one level down. So that's going to be equal to dx of x over dx plus a. This is your integration constant, right? Okay, then we are not done yet. Okay, so that's simplified, like do the integration. We just did the integral. That's what happened there. Now the next thing we're going to do is we're going to take another integral. So, oops. Dx x over dx plus a. And remember, it works like this. You apply it over the whole thing. Right, so we're going to integrate again. Take another integral. And now we can distribute. That is equal to the integral dx of x over dx plus the integral dx. Oops, no, that's partial. X plus the integral of a dx. Right, this is distribute. Integral distribution is allowed. Equals x of x. Right, so these cancel out again. Plus a new integration constant b plus ax. Right, so we did the integration. All right. Then we set it equal to 0. X of x plus b plus ax equals 0. All right. Great. Next we can solve for x of x. How do you do that? You move it over to the other side. So x of x equals negative e minus ax. Now, we're going to play a little trick. So if something's a constant, that just means it's a number. But we didn't know which number it was anyways, because it's a constant and it's an unknown. And now we have these negative signs. Well, what if we just folded the negative sign into the constants? We don't actually know what it is yet anyways. Well, we could do that. So let's go ahead and do that. So what I'm going to do is I'm going to say x of x equals a x plus b. Right, I folded the negatives. All right, so what did I do here? So I set it equal to 0. And I, in order to solve for x, what I did is I subtracted. And what did I do here? Fold the negative into the constants. And then I rearranged. All right, that is for 1/2. We also need to repeat this whole procedure for the other side. And this is going to go pretty similar to how it went on the other side. So we need to repeat. All right, so I'm going to go ahead and go through this one fairly quickly now because you've already seen how this has worked out. So we got, this is for the time solution. All right, we just did the position one. Now we're going to do the time solution. All right, we should probably mark this because we'll want to come back to this one. All right, great. So let's move on with the time side. So we're going to do d squared t of t over dt squared minus kv squared t of t equals 0. And then what we're going to do is we're going to out, right? Let's let k be 0. So now we do 0. So to do that, we do t of t over dt squared minus, and we're letting k be 0, so that will be 0 v squared t of t. So this whole thing is gone. It's 0. And now we have d squared t of t over dt squared equals 0, and that's to simplify. And now we're going to solve by integration again, instead of using the longer version of the equation. So here we're going to play the same trick. So we're going to do the integral of d squared t of t over dt squared the dt, that's for the partial, by the way. All right, so we're going to integrate, and then we're going to say that's going to be equals. So when you integrate out, you lose 1 power. So you got the t of t over dt plus a, your integration constant. And then we're going to integrate again. So we're going to do the integral of dt. Why do I keep doing this? Sorry. technically not correct. Okay. The integral of dt of t over dt plus a dt is going to be equal to the integral of dt of t over dt plus dt plus the integral of a dt, which gives us t of t plus the next integration constant d plus at, and then we set it equal to 0. T of t minus b minus at equals 0. And this is 0. Then we do similar things. Oh, no, this is wrong. These are pluses because they were originally. Let me just double check my signs here. When we come out of doing this, it's pluses. And we set it equal to 0. Yeah, okay, those should be pluses. Okay, this is true. Oh, yeah, okay, this is if and only if A2 equals 0 and B2 0. QT equals. Quite right. Just want to make sure I didn't make any copy errors here. T of T. A2T. Oh, I just switched the order. All right. Sorry, I'm going to just make a little adjustment here. I'm just switching the order of the terms, that's all. I was trying to figure out why it didn't exactly match my notes, and that's why the order was different. Like that. Okay. Definitely, if A2 equals 0 and B2 equals 0, right? The only way you can sum things up and have it equal to 0 is if the sum of those things is 0. So we have this idea of, oh, yes, that would make sense. T of t plus b plus at equals 0. Yeah, hold on. There's, yeah. I also accidentally flipped too many pages at once, which is why this is a little messed up. I apologize for this. Basically the same thing that I just wrote here. Solve for t of t. T, t of t equals negative b minus at. Yeah, that makes more sense. But these should be plus signs, and we have the minus signs. So again, we're gonna just play that same trick to absorb the negative sign into the constants. So we have t of t equals at. There, I just switched the order, plus b, like so. And now we have two equations. two equations here, resulting from what we've just taken a look at. All right, so let's just recap a little bit, right? So we needed to solve the differential equation, which we were able to solve easily because we realized that we could just integrate because these were kind of easy ones. And so we did that. And we also had separated out the differential equation. So we had a time-dependent one, and we had the position one. So the answer for this one up here, this is our position one, and this is our time one right here. So we have these two solutions. So now, just like we did last time, we could apply the boundary conditions to determine the values of the integration constants. That's the next thing that we would want to do. Just like we did the last time. Apply boundary conditions. To determine the values get the values of the integrations. Recall that this is still on a equals 0, and there is k is less than 0 and k is greater than 0. Don't forget that. Alrighty, so let's go ahead and see if we can do this. So we're gonna have x of x equals a1 x plus b1. This is given. This was our solution from above for the position half. All right, now we have t of t equals a to t plus b2 given. Solution above for time half. And we have u of 0 and t equals 0 for all t. And we have u of L and T equals 0 for all T. These were the boundary conditions. Which we discussed before. Okay, so that's these two. And we also have another piece of information, which we're going to pull from above as well. U of x and t equals x of x times t of t. This was our separability assumption. From above. So now what we're going to do is we're going to substitute in the boundary conditions. We have two of them. U of 0 equals x of 0, t of t equals 0. All right, so x of 0 equals 0, or t of t equals 0. Right, this is a property of 0. How do you multiply things together to get the answer to be 0? Well, that means one of the two things is going to be equal to 0. So x of 0 is 0, or t of t is 0. T of t equals 0 doesn't make any sense. What does it mean? T of t equals 0 says time is always 0. That is, the clock never advances. That doesn't make any sense. So this is an extraneous answer. Therefore, this is the math symbol for therefore, x of 0 equals 0 must be the solution of interest. All right, x of 0 equals a1x plus b1 equals 0. This is if and only if a1 equals 0 and b1 equals 0. This solution implies that x of x equals 0. The position is always 0. In other words, the wave never has any displacement. That also doesn't really make a lot of sense. So if the wave doesn't move, and the displacement is 0, and the time never advances, then nothing happens. This is a trivial solution. All right, but we have another trial we could make, right? What about the time equation? Remember, we've just done the position equation. There's also the time equation. So we could also do that. So we can substitute in the boundary conditions. to the time equation. So we're going to have u of L and t equals x of L. So this is very analogous to the one we just did. So I'm going to just move along a little bit quickly on this one. This is x of L equals 0, or this is the same reason t of t equals 0. T of t equals 0 again doesn't make sense. This is again extraneous, it doesn't make any sense. The time is always 0. So therefore, x of L must equals 0, must be interesting. Be of interest. So we're going to solve this one. So we do go ahead and solve this one. And this one also yields a trivial solution. So I think I'm gonna go ahead and just leave that one for you to solve in the interest of time. So you can plug in. You can plug in yourself, right? And this also gives the same result. So in other words, for k equals 0, we only get trivial results. But remember that we also have k is less than 0, greater than 0. All right, so I think this is where we're going to pause on our math discussions for today. Let's just let's take a moment to just review what we have talked about. So we saw that we want to solve a simple problem that has to do with solving the equations. Now, about that, we have the situation that quantum mechanics is really hard to solve, and a lot of those equations require some pretty fancy math. So what we might want to do is we might want to start off with something a little bit easier, which is the one we were doing today. This is the easy version. And today's was about the classical wave equation. And so a lot of the things that come up in solving quantum mechanical problems already come up in doing the classical wave equation, which is pretty much the simplest situation you could have. So what we saw is that what came up was the separation variables, because unlike the equations that we were doing last time, we have more than just one variable. We have x and we have t. And if you go into more dimensions, you have even more things, and you could be working not in just x, y coordinates, but you could need to work in polar coordinates. I mean, there's so many other things that could happen that would make it even more complicated to solve these kinds of things. So this is why we're solving the ones that we are, and why we're actually pushing the numbers and doing these hand calculations for these ones, because these ones are actually solvable. And as we'll see when we get to hydrogen, very quickly things become not solvable because a lot of the assumptions that we're making would be violated, like separability doesn't hold, for example, would really ruin being able to solve this. And so that's why, for example, we have computers that are able to solve for these things, and you can't solve anything in quantum mechanics beyond hydrogen. So what we saw today is we saw how to deal with doing the separability to separate things out so that you have two separate variables, and we demonstrated that you can actually separate these out. But then you have the problem that you're carrying along this constant k that does keep them linked. So I mean, they're not actually linked in terms of taking the derivative, but they are related to each other by this constant k, which has then been following us throughout all of this, which has then led to all these problems that we now need to consider. What is the separation constant k's value? Because when we solve, the value of that actually becomes really important, and it also links the two of them together. So we have the three cases: it's negative, it's positive, or it's zero. So we got to the point where we tested out for k equals 0. I mean, the great thing about that is when you set stuff equal to 0, oftentimes lots of things drop out of equations, which is a lot of what we saw today. And so instead of having to actually apply the second order linear homogeneous differential equation procedure, we were able to just actually solve by integration, which was really nice because our terms were really small and we could just do it that way. But you could, of course, go back and solve it the hard way if you preferred. And don't worry, we'll have opportunities to do that coming right up. But today we took a little break and we solved it a bit of an easier way. It also helps us keep remember what those calculus things actually mean and why we're applying the equation that we did. Okay, so we did that. But we only got to k equals 0. And what we discovered is that when we apply k equals 0, we actually do get some answers, but the answers are all trivial cases. So the trivial cases that we found is that either the time never advances, so if you never actually have any time, then the wave can't propagate because there's no time to propagate it. And the other thing that we saw is that the other case was that there's no displacement. So it's not very exciting to have a wave that doesn't actually have any displacement. So basically, up to this point, we've only been able to solve for some trivial cases. But don't forget that we haven't tested out the other case. So those are the things that we would want to take a look at. So we will need to follow the same procedure that we did today, but try for different values of k and see what the outcome would be. So spoiler alert, there are actually interesting displacements of waves in classical mechanics. And so we will take a look and see what those solutions look like the next time. And then just looking ahead to what we'll be doing beyond that, we would also be taking a look at some of the other kinds of equations. So we'll hopefully be getting to particle in the box and the Schrödinger equation soon after we deal with solving this classical equation, and we will be seeing how the similarities of solving that also pertain to, well, what we've been doing here. All right, well, thanks so much for joining me today. It is New Year's, so I'll go ahead and wish you a Happy New Year's by the time you actually see this. It probably will not be New Year's anymore, but today is January 1, 2025. So wishing you all a great day. Hope you had a great day, and looking forward to continuing our discussion on the classical wave equation and continuing on with quantum mechanics and physical chemistry for the life sciences coming up in our future lectures. Signing off. All right, stop recording.